And we should be live.
Okay, so I think we can start the session. So welcome everyone to the morning session. The first speaker will be Arnaud Sangnier, and he will speak about distributed memory automata. Please start.
Okay, so thank you for letting me the opportunity to present this work. And first of all, I hope you are all fine and it's not tough for you to live through these times. So this is a joint work I've done with Benedikt Bollig, which is in LSV, and Fedor Ryabinin that did an internship with us and now is in EMDA in Madrid. So what are the motivation for these talks? The goal, okay, it's instead in a project where we are trying to discuss with people that develop distributed algorithm, and we want to find model for classes of distributed algorithm. So first, when you look for such model, you have to take different features into account, whether it's message passing or shared memory, whether the execution is synchronous between all the processes or asynchronous, whether you know the number of participants or you don't know the number of participants, whether the data that are manipulated in the system are for a finite set or from an infinite set, and so on and so on. And then once you have this model, the goal is to develop some automatic verification techniques or some automatic analysis technique. And the problem always with this kind of theory is that you have to deal to find a trade-off between what you can express in your model or with your specification and the feasibility of the verification. So what can be done in practice? Because often, if your model is too expressive, you will have some undecidability. And okay, and if it's too easy, maybe you cannot model some aspects of the algorithm. So it's really you are at the edge between expressivity and feasibility of the verification. So an example, so where does this work start from? It starts from this algorithm which is called renaming algorithm. Okay, so I just say it directly. I'm not able to verify automatically with the technique I will present in this work, this algorithm, but it gives us insight of what could be some aspects we need to take care of in order to go towards the verification of such algorithm. And so I don't ask you to read in the details this algorithm, but what is interesting is what are the properties we have. So first, this algorithm is designed to run with an unknown number of participants. So this means that you can have many entities, and no matter how many entities you will have in the networks, this algorithm will work and will terminate, and it will compute this renaming. So just for your knowledge, renaming, it says, for instance, you have all your address or IP address or your MAC address, and then you want to come with a set of address or a set of new names that is smaller than all the big sets. So assume you are with n participants, and maybe you want to have a value for your identities that are up to 2n and not all the IPs. So this is, so then if I come back to this algorithm, so it's designed to run with an unknown number of entities. It manipulates IDs from an infinite data set. You have this you have a shared memory. So this means you have some register where you can write and read value. And you have this snapshot operation, which consists in, I can, in an atomic way, take a picture of my shared memory, and then I can reason on this picture, on the scan memory. So this is an important feature. This is something that can be achieved with some distributed, it's like a macro, but you can do this. And so we took this characterization, we said, okay, what kind of model could we reason that keeps these things on, and what could be a model where we could have some properties, and what would be the complexity, and so on, and what would be method to analyze such model. So in fact, we take this, and first we extract a simple model, so with a parameterized number of participants, where you have some shared registers, where you manipulate data from an infinite sets, and you can test on the shared register, and our tests are inspired by snapshots. So I will explain later on what it means inspired by snapshot, but basically it means that instead of locally doing a snapshot and then doing a test on the scan memory, it's more or less equivalent to say I can do a test atomically on the shared register. So the difference between that, in fact, a test CC does not change the value of the shared register. It does not matter whether you scan and then you do the test or if you do the test atomically, because anyhow, the test that you do on the scan memory, you do it locally in the distributed system. And what is the problem we study? Okay, since it's a first step, we study a classical problem, which is a reachability of a control state, or it can be seen as reachability of a bad state. And the question we ask is that, is there a number of participants such that with this number of participants in the network, I have an execution where a process, one of the processes that is in the network, visit a given control state. Okay. So it's everything is existentially quantified. I look for a number of participants, I look for an execution, and I want one process to visit the states. So this is why you have to think of the state as a bad state. In other words, I want to know whether there is a network where something bad could happen. So what is the model? So inspired by memory automata, we have this what we call this distributed memory automata. So morally, it represents like a finite state protocol. So you have a finite state automaton. You have a single initial state that is the entry point of your algorithm. You have some final states that can be seen as the bad states. And your edge are labeled with two types of instruction. So, or you can update the local of the shared register. So I will show you in the next slide, each process in my network has a local register and a shared register. Or you can do some test. So it's at this moment, from the syntactic point of view, a distributed memory automaton is only a finite state automaton labeled with either null, right, or some test of the form equal k, different of k, strictly greater than k, strictly smaller than k. And how are these tests used? First, I need to explain you what is a configuration for a distributed memory automaton. So it's you have n processes. So, and each process is equipped with one control state, which represents which state of the automaton is, one local register that is single writer, single reader. What does it mean, single writer, single reader? It means only this process can write and read into this register. The other processes do not have access to its local register. And then you have n shared register. This is the shared memory, which are single writer, multiple reader. What does it mean, single writer? It means only the process can write to its own register, but all the other processes can read all the register. So basically, you have a distributed system where each process has its local memory and a shared memory that everybody can read, but each process can only write in his own index register. And what is an initial configuration? So an initial configuration, it's all the processes are in the initial state of the distributed memory automaton. In their local register, they all have a different value that can be seen as their ID. And in the shared register, I have an unknown value that is different from all the others. So I put bottom, okay? So it's like the shared memory is empty at the beginning. And what is the semantics? So now, so you have an execution is a sequence of configurations that begins with an initial configuration. In an execution, the number of processes stay constant. That means that if I begin with a configuration with n processes, I will have these n processes all along my execution. And at each steps, I reason in an interleaving semantic. So at each step, one of the process does an action. So it does an action of the automaton. And it does an action for Q to labeled with A to Q prime. It has to be, this process, it has to be in the state Q. It changes its state from Q to Q prime. And what are A? So it depends. If A is a new value, is a new, so if the action is new, it means it writes a new value in its local register. And what is a new value? It's a value that is not present in the shared memory. So globally, what it means is new, it means I scan the shared memory and I take a value that is not present in this shared memory and I put it in my local register. Then you have the write. So what is the write? It means when I go from Q to Q prime and I do a write, I write the value that is in my local register, I copy it into my shared register. And then I have the test. So what is the test? I test if my local value, the one that I have in my local register, how many times it is present in the shared register. So it's equivalent to doing a scan of the shared register and I testing the value I have in my local register, how many times. And of course, this is the only broken transition. That is, if the value is not present, for instance, assume the test is equal to k. If my value is not present k times in the local register, I cannot take this transition. So let me provide you an example. I hope it's, so the slide is a bit full, but so I have the distributed memory automaton I have given at the beginning of the talk. So at the beginning, all my processes are in the initial state Q0. They all have a different value in their local register. So here I took 1, 2, 3, but it could be any natural or any value. I mean, it's not necessarily natural, but the important is that they are all different. And in my shared memory, I have a bottom to say, okay, the value, none of the values that I have in the local register is present in the shared memory at the beginning. And then what can I do? So to follow well, each time I do an execution, I say the action that I do above the arrow and the number of the process under the arrow in red. So you see I have numbered my processes from 1 to 3. So let's say the first process from Q0, it can go to Q1 and he do a write. So what does it mean to do a write? It means it takes the value of its local register and he writes it in the shared memory. Then the second process, which is as well in Q0, can also perform this write. And so we reach this configuration here, where the second process is instead Q1, and in the memory, he has written his value 2. Then now, what is interesting is that the first process from Q1, it can do, there is a bug in my, okay. Let's say from the end of the execution is not correct. No, I see it. But from the first, from Q1, it can do a new. And what is interesting is that it can take a value in this local register. It can put a new value that is not present in the shared memory. So now in my shared memory, I have 1, 2, and bottom. So I could, it's not deterministic, but I could take 3. It means the same value as Q0. Because 3 is not present in the memory. Then the third process, which was in Q0, can go to Q1 and write the value in the memory. And it's here that there is a bug. So you have to imagine that, in fact, there is an error from Q2 to Q1 with a write. So I didn't take I should go to Q3, but I made a mistake. So here now, when the first process could write to the memory, let's say, it's not in the automaton, but it writes its value, and now I have, okay. I have to wait that this disappear. I have the 3 value in my memory. So I have 3, 2, 3 in my shared memory, and I can take the test equal to 2 to go from Q1 to Q4, because the first process, which has 3 in this local register, the 3 is present 2 times exactly in the shared memory. And then I reach a configuration where I am in Q4. And this is what I call the finite configuration, because I have one of the processes that is in a final state. So I'm sorry about this. What I mean is here I should have, to be correct, an edge between Q2 and Q1 labeled with write. So just as I said, a remark is that new and the test are equivalent to perform a snapshot on the shared memory and test a constraint on the scan memory. So this is a comparison with K. Or choose a new value not present in the scan memory and a new, and only instead of in the model making the snapshots and reasoning on a copy, we decided to do this operation atomically on the shared memory. And what is the problem we study? So we studied 2 problems. The first one is the reachability. So you give a distributed memory automaton, and you ask, is there an execution from an initial configuration to a final configuration? So if you want to interpret it, is there a number of processes where I take an initial configuration with this number of processes, and I can find an execution where I reach a final configuration that is one of the processes is in the final state. And the variant of this is that what happens if we fixed the number of processes. So now you have a systems where the number of processes is fixed, is n, and now you want, it's the same question as reach, but only you want that the initial configuration has n processes. So you begin, you know the number of processes somehow. So just some example, if you take this system, okay, can Q4 can be reached? So to reach Q4, what you see is that I have to do a test equal 1 and equal 2. So intuitively, how does it work? I take two processes. They first guess they do a new, and they write in their local register the same value. This is allowed because this value is not written in the shared register. Then one of the two writes this value in the shared memory. So now he can go to equal to 1 because he has written his own value in the shared memory. So this value is present exactly 1. And then the other process writes the same value to the shared memory. So now the value is present twice. And so the first process can go to Q4. If now I take the same protocol, but I change the order between the test equal 2 and equal 1, what you see is that, again, the two processes can take the same value. They both write. Then they both can take the equal to test, but none of them can go to Q4 because to go to Q4, it means that one of the processes that has written its value in the shared memory can overwrite it with another value. But it's not possible because they are both in Q3. So in this system, I cannot reach Q4. And a way to reach Q4 will be that, okay, when I am here, one of the processes that is here is able to do a new and a write to overwrite the value he has in the shared memory to another one, so that to make the number of copies in the shared memory go from 2 to 1.
Excuse me, like 2 minutes left.
Yes.
Oh, yeah. So.
2 minutes left. Sorry. So what? So the result we have. So I'm not going to go. It's that first fixed reach is p-space complete, and the proof is that when you have the number of processes that is fixed, in fact, you don't need more than 2n+1 data value in all the system. Okay, you can do a simulation with exactly this number of values. So finally, you get a finite state systems which is of exponential size, but each transition in these systems can be computed in polynomial time. So this is why you get a p-space algorithm. And the lower bound is that it's a bit tricky, but you can reduced to the intersectional emptiness of M-finite state automata. And so here I have an example where I explain to you the difficulty in this model is to go from when can I decrease the number of value in my shared memory. So here, if I want to reach F, I have 5 times the value in my shared memory, and then at some point it has to go from 2. It means that 3 processes that has the same value as me in the shared memory has written this value. And the main result we have is that we can solve reach in p-space. And the idea of the proof is that we compute iteratively 2 sets of states. We compute the set of states from which a new can be done, and we compute the set of states from which a new and then a write can be done. So NW, it's the set of states from which you can overwrite your memory, and N is the set of states from which you can guess a new value in the memory. And how we compute these 2 states is that we simulate this distributed memory automaton with a single value. So it means now we look only at a single value. And when you do a new, it means that you choose this value. Then when you do a write, you write this value in the shared memory. And when you are in a state which is in new write, means you overwrite this value and you leave the system. So we only look at some phases of the protocol with a single value. Yes, I've seen you. I will jump to my conclusion because, okay, so the idea is that we have seen this problem. So it was very interesting for me to introduce the model. We have proved that fixed reach is p-space complete and reach is in p-space. We don't have any lower bound, so it might be improved. And what we plan to do is, okay, how to extend these techniques to verify this algorithm so that enter in this family. Can we verify more complex properties and only reachability? Also, it could be interesting to understand what can we achieve in terms of distributed computing with such model. And also something that we did not look at carefully is that whether our decidability proof implies a bound, reasonable bound on the number of processes needed to reach control states. Because at the moment we reason on some abstract systems and our method at least not directly provide a bound. So thank you for listening to me.
Thank you very much for the talk. Are there any questions? So please raise your hands to let me see if any one of you want to ask. Meanwhile, maybe I'll ask. I'm surprised that the complexity seems to be lower without the bound on the number of processes.
Yes.
Why so?
It's something that often happen in parameterized systems. So
Okay.
the trick is that somehow you can use the fact, let's see, for instance, you want to have a witness for an execution. You can use the fact that you have parameter to take processes on demand to build your execution. And somehow this witness execution, I mean, I think it could be in NP and maybe in P.
Okay, thanks. And are there any questions in the audience? If not, I'd like to ask about the model. What about extending the model? I'm not sure if it makes sense, but imagine many local registers, more than one local register, or maybe order data and some extra tests on the order. Did you consider this kind of extensions?
Yeah, I think it will make sense in particular to see more features on distributed algorithm, because sometimes with this model where you have data and you only do snapshot and write to the memory, you have to take, for instance, the smallest value that is in the memory or the biggest one. So the important thing is that you rarely compare value 2 by 2. So at least only equality or disequality. But sometimes you need to say, I take the minimal elements. Okay, let's say you want to, everybody gets a new ID, and the one that wins is the one with the smallest value that he has guessed, for instance. And if there are more than 2, they all again begin like a competition to find the smallest value and so on. So it could be extended this way. It could be extended also like the example I just gave with probability. So like to avoid like conflicts, if you have guessed twice the same value, you flip a coin and you show that with probability 1, you will have a new value that is different from the other guy.
And I guess it's about complexity of these extended versions.
Yeah, this I don't know. I think it will be nice to study more these models.
I see. Thank you. I don't see any volunteers to ask other questions, so let me thank Arnaud for the very interesting talk. Thank you, and let's proceed to the next one. The next talk will be given by Daniela Petrisan. So please share your screen with us, Daniela. The talk will be on the abstract categorical approach to automata learning. So very interesting talk. Please unmute yourself, Daniela, if you can.
Yes, I was not co-host yet, so now I am.
I see. To share the screen, you need
I'm sharing the screen right now. Can you see my screen?
Yes, I do.
Okay.
Good.
So I can start whenever you want me to.
I think you can start. So please go ahead.
Okay, thanks a lot. So this talk will be about learning automata and transducers, and it will be about a categorical approach to these topics. It is joint work with Thomas Colcombet and with Riccardo Stabile, who is a master student from Milano who joined us for an internship. So there will be not a lot of category theory in this talk, but I will try nevertheless to incite you to read our paper and to see how category theory gives a unifying approach to learning various forms of automata. And in doing so, we highlight the link between learning and minimization, and we managed to reuse some off-the-shelf results from a functorial approach to minimization that I have introduced in previous work with Thomas. So automata learning is a classical subject. There are many applications in verification, ranging from adaptive model checking to interface specifications in Java. So there are many surveys out there. Here is one of them, where you can read more about applications of learning. And the most famous algorithm for learning is perhaps Dana Anguin's L-star algorithm, which introduced in 1978. In the next few slides, I will try to recall this L-star algorithm. So the goal is to learn a regular language of words, L, and the algorithm or the learner interacts with a teacher or an oracle that knows L, and the learner can ask two kinds of questions. So first, there are the membership queries. You ask, does a word belong to the language? And the teacher says yes or no. Or you can ask equivalence queries if you give the teacher a hypothesis automaton, and the algorithm asks whether this hypothesis automaton accepts the language to be learned. If the answer is yes, then the algorithm finishes. If no, the teacher has to provide a counterexample. So a word which is accepted by the hypothesis automaton but is not in the language, or vice versa, a word which is not accepted by the hypothesis automaton despite being in the language. And this algorithm stops when the teacher agrees that the hypothesis automaton accepts the language L, and for regular languages, it does so in finite time. So here are a few definitions that will allow us to understand the algorithm. At each stage in the algorithm, we'll have two sets of words, Q and T. They are both initialized with the set containing only the empty words. And you can think of Q as a potential set of states for the hypothesis automaton. And you can think of T as some test words, which are used to approximate the Michael-Narodi equivalence relation. So this T equivalence is defined as follows. We say that two words W and V are T equivalent if and only if for every word U in T, WU is in the language, if and only if VU is in the language. So you can see that if T is the whole A star, then we would get here the Michael-Narodi equivalence. And in order so such a pair of sets of words QT gives rise to a hypothesis automaton, provided that it satisfies that it has two properties. The first one of them is closeness, which is defined here. So we say that for every Q in Q and for every input letter A in A, there should be a P in Q such that P is T equivalent to QA. And the second property is consistency, which means that for every two states Q and Q prime, two words Q and Q prime in Q, and for every input letter A, Q is T equivalent to Q prime, implies that QA is T equivalent to Q prime A. And when QT has these two properties, so both closeness and consistency, then we can build the hypothesis automaton HQT. So in a nutshell, this is the L-star algorithm here, and we will see how it works on an example. Let's assume that we want to learn the language consisting of only the word A over a very simple alphabet. We only have one letter A. So to begin with, Q and T are both initialized with the set containing only the empty word. We check whether QT is closed and consistent. In this case, we can see that it is not closed. Why is that? So from epsilon, if we want to perform an A transition, where do we go? We cannot go to epsilon itself because epsilon is not epsilon equivalent to A. Epsilon is not in the language, whereas A is, and there is no other state. So the only solution is to enlarge the set Q, so we add an A here. Then we check whether this pair, so now epsilon A and epsilon is consistent. In this case, this is fine. We don't have to add anything to T. And now this pair is actually closed and consistent. So from A, if we want to do an A transition, we reach epsilon. Epsilon is epsilon equivalent to AA because both of them are not in the language. So being both closed and consistent, now we can construct the hypothesis automaton out of this pair of sets. So this is the automaton. Epsilon is the initial state. And then A is the only accepting one because A belongs to the language L. So we have our automaton and we ask the teacher, is this automaton accepting the language that I want to learn? And the teacher says, well, no, because here it is a counterexample. You look at the word AAA, which is accepted, and it is obviously not in our language. So we have to add this counterexample, AAA, as long as with all its prefixes that are not already there, to Q. So now Q is this 4-element set, and T consists of epsilon. So we have to go back and check, is this pair closed and consistent? We can check that closeness is fine. On the other hand, when we get to check consistency, we have an issue. Epsilon is equivalent to AA, but if we perform an A transition from both these states, then A is not epsilon equivalent to AAA. So this means that the set T is not, the test words are not sufficient. In fact, we have to enlarge this set. So we add an A here in the set T. So now this is closed and consistent. I won't do all the checks, and we can construct again a hypothesis automaton. So we have to quotient some states words in Q. We have this 3-state automaton, and when we ask again the teacher if this accepts the right language, the teacher says yes. So the algorithm finishes and returns this hypothesis automaton here. So this is in a nutshell the L-star algorithm, and it is a very versatile algorithm that has been generalized to many settings. So we have versions of it for weighted automata, for subsequential or sequential transducers, for nominal automata, symbolic automata, non-deterministic automata even, and alternating automata. And this is a quote from a work of Bollig et al. That says that we should have a unifying framework for all these versions of learning techniques. Probably the authors were referring to the LibAlf and the libraries for implementing these techniques, but I think that also a theoretical framework is very much needed. And we are not the first to do this. There are some orthogonal category theoretic approaches, the CALF project of Van Herd et al. And other approaches of Urbat and Schroeder. In our work, on the other hand, we use, as I said before, a unifying framework for minimization, which was introduced in our previous work with Thomas. The idea here is that we look at various forms of automata in different categories, and we can look at this automata by interpreting the same diagram in various output categories. So for deterministic automata, we will use an output category, the category of sets and functions. For non-deterministic automata, we will use the category where objects are sets and arrows are relations. For weighted automata, the category of K-vector spaces and linear transformations. And for subsequential transducers, a category of free algebras for some partial actions of monoids. I won't have time here to introduce this, but you get the idea somehow. So all these forms of automata, so they are forms of word automata, and for an input letter A in the alphabet, in the deterministic case, here we have a transition function, here we have a transition relation, here we have a linear transformation, and here we have some other kind of morphism of algebras. And we see this pattern emerging that allows us to regard automata as functors from some 3 object diagram to these output categories. And when possible, we identify sufficient conditions on these output categories that allows us to give a unifying framework for minimization. So this is all I have time to say about this for this talk. But we will use this framework also for minimizing some forms of automata that are relevant for our L-star algorithm. So if we look again at the L-star algorithm, when we are in the stage QT of the algorithm, so remember these pairs of states that pairs of sets of words that we need, we only have access to a fragment of the language. So I know if a word which is of the form Q, for some Q in Q and appended to T for some test word T, we know whether this one is in the language or not, or we know whether a word which is in the set QAT, so it is of the shape Q, some input letter A followed by some test word in T, belongs or not to the language. So we have this small fragment of L, which we call LQT, which is known at this stage of the algorithm. And at each stage of the algorithm, we will also need a notion of Qt by automaton in our generalization. So what is this notion? You can imagine that we have an automaton where we have two sets of states, Q1 and Q2. We don't have an initial state, but rather for every word in Q, we can reach immediately some state in Q1. If we are in a state in Q1 and we read an input letter in the alphabet, we go to some state in Q2. We also have some epsilon transitions. So from a state in Q1, we can go to some state in Q2. And finally, when we are in a state in Q2, and if we read some test word in T, we know whether we accept or we reject. So we have this notion of Qt by automaton, and we will be interested in those Qt by automata which accept the language that we have here. And of course, we also need some coherence conditions. Namely, if I have some Q in Q such that QA also belongs to Q for some input letter A, then first going to a state in Q1 by reading the word Q and then making an A transition to Q2 should lead us to the same state in Q2 as if we first read the word QA, go to some state in Q1, and then perform an epsilon transition to go to Q2. And a similar condition should hold here if I am in Q1 and if I make an A transition to a state in Q2. If I read now a word T, then I accept if and only if, on the other hand, by going from the same state in Q1, by performing an epsilon transition to Q2, and then by testing with the word AT, I accept again. So this diagram should commute again. And this notion of Qt by automaton, I have illustrated here. So this is relevant for the original L-star algorithm for deterministic automata. But you can also interpret Qt by automata in an arbitrary category under some mild assumptions. And this is the kind of automata that will be used in the generic L-star algorithm that we have provided. And in this generic setting even, we can use the off-the-shelf results from the previous framework that we developed with Thomas to have the minimization of the Qt by automata that accept the language L. So here is the computation for the case of deterministic Qt by automata. What is this this minimal by automaton accepting LQT? What is this? The first set of states is Q quotiented by the T union AT equivalence relation. The second set of states is Q union QA quotiented by the T equivalence relation. So if I am reading the word Q, I will go to the equivalence class of Q with respect to T union AT. If I am in here, in the state which is the equivalence class of Q, if I make an A transition, I will go to the equivalence class of QA with respect to T. And most importantly, this epsilon transition, which will play quite an important role. So if I am in the equivalence class of Q with respect to T union AT, if I make an epsilon transition, I will go to the equivalence class of Q with respect to T. And finally, the last arrow here, so if I am in the equivalence class of Q, upon reading a test word T, I accept if and only if Qt belongs to the language. Similarly, if I am in the equivalence class of QA and I read a test word T, I accept if and only if QAT belongs to the language. And as I said, this epsilon transition of this minimal Qt by automaton plays a very crucial role. We can check that this is surjective if and only if Qt is closed. So you remember so this is the L-star algorithm that I have recalled here. And you remember these closure conditions that allows us to perform the transitions from some state in Q. And finally, epsilon min is injective if and only if Qt is consistent. So in fact, this epsilon min is an isomorphism provided that Qt is closed and consistent. And in this case, you can see that being here an isomorphism, we can merge these two states, and we can obtain the bioautomaton, from this bioautomaton Qt, the hypothesis automaton, which has a set of states, either the quotient of Q by the equivalence relation corresponding to T union AT, and this is of course isomorphic to the second state given here. So all this computation, I should say, works in category C that have some very mild conditions that allows us to do this minimization. And what is fascinating is that when you look at what it means for epsilon mean to be an isomorphism in the category, for example, which is used to represent subsequential transducers, then you obtain precisely the conditions that generalize closeness and consistency in that specific case. So this really instantiates to the algorithms that exist already in the literature. So here is the generic algorithm, the fun L-star algorithm, which is the main contribution of our paper. It looks very much like the L-star algorithm, except that now the language L is actually interpreted. I didn't have time to give all the details of what this means, but it is interpreted in some category C with some mild assumptions. The output is again the minimal automaton accepting L, and it works just as before. So we start with epsilon for both Q and T. So Q and T are again two sets of words. And now instead of closeness and consistency, we have this condition of, so the epsilon min, this epsilon transition of the minimal Qt bioautomaton, this should not be an isomorphism. So this is what generalizes Qt not being closed and consistent. Now, epsilon not being a surjection, what we have seen in the case of deterministic Qt bioautomata, or closeness not being closed, the pair not being closed, this is generalized by saying that this morphism does not belong to a class of morphism, which is part of a factorization system on our category C. So this is generalizing surjections or surjective linear transformations or some form of quotients to a category. And you may have guessed, so here we had in the original algorithm not being consistent. We have seen that this for Qt deterministic bioautomata meant epsilon, or the epsilon transition not being an injective. So in a category, we say that this doesn't belong to some class M, which is also part of this factorization system. And when epsilon is an isomorphism, which means that it belongs both the intersection of E and M, then we can form this hypothesis automaton by merging the two states of the minimal Qt bioautomaton. And we can ask an equivalence query. If the answer is no, then we enlarge Q by the counterexample and all its prefixes. We do this until the answer is yes. And when we get an yes, we return the hypothesis automata Qt. So here
Excuse me, just 1 minute left. So
thank you, Slavomir. I think I'll be fine. Here is the correction and termination of the algorithm. So the theorem works assuming that we have some category C endowed with a factorization system EM with countable powers and copowers. So these are some special forms of limits and colimits. And then we consider a language L in this category C. We should have some condition which generalizes the regularity of L from the L-star algorithm. We represent this by saying that the state space of the minimal automaton should have this EM Noetherian, so it should be EM Noetherian. This means that there are no infinite chains of E quotients and of M subobjects. And under these assumptions, then our generic algorithms terminates, eventually producing the minimal automaton that accepts the language L. So to conclude, we have this generic algorithm which instantiates almost immediately to deterministic automata, weighted automata over fields, to subsequential transducers. We also have an optimized version of fun L-star. So you may have noticed that in our algorithm, I added AT to T or QA to T, but we don't need to add all these sets to T. We may just select a good letter, and we can do this as well. There is a long archive version of our paper where you can see the details for this optimized version of the algorithm. And then for future work, we can consider extensions where instead of the classical sequential transducers, we look at situations where the output monoid maybe is not free, and also something which is not encompassed in our current work. What about nominal automata and other forms of automata where we may need to actually change the shape of the input category? So I think I am done. I am stopping here. Thank you so much for your attention. And,
thank you very much, Daniela. I enjoyed the talk.
Thank you.
Do we have any questions? Please raise your hands. I see two hands raised, I guess. Please go on. Anyone who wants to ask a question, please unmute yourself because I'm. No, there's no one. Okay. So, I'm very curious what prevented you from capturing register automata or bit-finite automata.
Well, it's just that the structure. So if you remember this word automata, that slide that I had where I was describing deterministic or weighted automata or subsequential transducers. So all of them had this category I where we had arrows only for input letter A. So it is a very special input category that we are using. And to capture, for example, nominal automata, we would need a lot more arrows somehow. And there is some form of enrichment probably that we should incorporate into the input category. I mean, I think it's doable, but we just did not have the time. And I mean, this was the first step already to encompass all this existing algorithm that I've mentioned. But yes, this is an obvious next step to go to orbit finite automata.
I see.
But it's just a lot of more work to be done, isn't it? there is a page limit to CSL.
Okay. Jean, please ask your question.
Yes, and thanks for the nice talk. I was wondering about the category theory behind that. So you said a word about it. You said that one of the conditions was that you didn't have any infinite chain of E quotients and M sub-objects, I think.
Yes.
That sounds very ad hoc. So I was wondering whether that could be expressed in another more synthetic way, perhaps, or whether you have necessary conditions that would be more palatable, or?
I don't know yet. I mean, what I can say about this is that the very same ad hoc condition also popped up in the work of Urbat and Schroeder, this Leaks 2019 paper that I mentioned, which uses some co-algebraic techniques. So it's not only us that are using this. It also instantiates to the right notions. I mean, it just means finiteness for sets, and it means finite sets in this Kleisli of T category that we are using for subsequential transducers, and it means finite dimensional vector spaces for vector spaces, for the category of vector spaces. So it really is finiteness or finite dimensionality in the standard way in the relevant examples. But it is true that we have not looked, and perhaps we should look whether there is some, I mean, what happens in some LFP category to see if there is a correspondence with finite presentable objects or something like this. But we did not investigate this carefully, I must confess.
Some kind of compactness condition, or I don't know.
Or something, yes. So if you have some topological flavor to your category. So yeah, it's something that we should investigate. Thanks for the question.
Thanks.
Great. Are there any questions from the audience? I don't see any. So thanks once more, Daniela, for the interesting talk. And
Thank you.
I suggest to proceed to the next one, which will be given by by Alex Rabinovich. Alex, please share your screen. The topic will be degree of ambiguity in tree automata. Okay, so please go on, Alex.
Thank you. Do you hear me? Yes, I will. Yes,
I hear you. I confirm.
Great. So we'll talk about degree of ambiguity of parity tree automata, and this is joint work with my student Doron Tiferet. And probably the oldest form of restricted non-determinism is unambiguity. So automata is unambiguous if on every input there is at most one acceptance around. For example, this automata is non-deterministic. There are two A actions which are going from this state, but it is unambiguous. On every input there is at most one acceptance around. And other degrees of ambiguity are defined in similar way. Automaton is k-ambiguous if on every input there are at most k acceptance rounds. It is boundedly ambiguous if it is k-ambiguous for some k. It is finitely ambiguous if on every input there are at most finitely many rounds. And countable ambiguous if on every input there are at most countable many acceptance rounds. And on finite words, on finite trees, every automata is finitely ambiguous. However, on omega words and infinite trees, some automata have uncountable or countable many acceptance rounds on the same input. So CSL considered the problem of deciding the degree of ambiguity of automata on finite words and finite trees. And he proved that there are polynomial time algorithms for deciding the degree of ambiguity of automata on words and on trees. That is, there is algorithm which decide whether automata is unambiguous, boundedly ambiguous, or finitely ambiguous, polynomial algorithm. And these results were extended to Buchi automata, so automata on infinite words, and also there is polynomial time algorithm for deciding the degree of ambiguity of Buchi automata on omega words. And we extended this result to infinitely, and we proved that there are polynomial time algorithms that decide whether a Buchi tree automaton is unambiguous, boundedly ambiguous, finitely ambiguous, or countable ambiguous. Buchi tree automata are less expressive than parity tree automata, which are equivalent to monadic second-order logic. And unfortunately, the main result of this paper is that for parity tree automata, the complexity is much worse. So here is our main result. The problem whether a parity tree automata is not unambiguous or is not bounded ambiguous, is not finitely ambiguous, is going to be complete. And if we ask whether parity tree automata is not countable ambiguous, we know that this problem is going to be hard and we don't have an upper matching bound. So this is main result of our paper. And here is the plan of my talk. So I will talk about k-dimensional parity tree automata and k-dimensional parity games. Our main results are about parity tree automata, but in order to prove this result, we need to use many dimensional parity automata. Then I will talk about ambiguity of parity tree automata, and I will show that this problem is going to be hard. And then I will show that the problem whether automata is bounded, finitely or countable ambiguous is also conp-hard. The proof of this result is obtained by reduction to the ambiguity problem. And I will conclude with the open problem and some further results. So let me start. What is k-dimensional parity tree automata? It is very similar to parity tree automata. It has states, alphabet, initial state, transition relation, and coherent or priority function. And transition relation has this type. So we are talking about automata over binary trees. And coherent function maps every state to k-tuple of natural numbers. And a computation of such automata on labeled tree is q-labeled tree. So the root should be labeled by initial state, and for every node, if we consider this node and two of his children, then the labeling should be consistent with transition relation. So here Q2, B, Q4, Q5 should be in delta. And accepting conditions or accepted computation are defined in the following way. Suppose with computation on tree T and pi is a branch in this tree. And we define by C pi phi the maximal colors that occur infinitely often in the ith coordinate of the sequence. So this is our branch. We are looking what states are assigned to this branch, and to every state we assign k-tuple of natural numbers. So we are looking to the ith coordinate and maximal state which appears infinitely often. And the computation of A on T is accepted if CIP phi is even for each tree branch and each coordinate I. And a tree is accepted by automata if there is an accepted computation of A on T. Now I will talk about k-dimensional parity games. Again, they are similar to parity games, but the winning condition is k-dimensional varied condition. We change winning condition. So we have places or states of the first player, places or states or nodes of the second player. We have edge relation and we have priority function. And now priority function to each state assign a k-tuple of natural numbers. And the notion of play, winning play, strategy, winning strategy is defined in a usual way. And the main technical result we rely on for the proof of our low bound is the following theorem. It states that the problem of deciding whether a node of the first player is in the winning region of the first player of k-dimensional parity game is complete. Okay, so let me continue with the proof or start with the proof that ambiguity of parity tree automata is hard. And in order to show this, we consider several problems and provide polynomial reduction between these problems. So the first problem is whether parity automata is ambiguous. Another problem is the intersection of two deterministic parity tree automata is empty. The next problem is two-dimensional deterministic parity automata empty. And the final problem is a node in the winning region of player one in two-dimensional parity game. We already mentioned that the last problem is hard. And we provide series of reduction from polynomial reductions from this problem to this problem, from third to second, from second to one, and concludes that the problem whether parity tree automata is ambiguous is going to be hard. So here's a plan of our proof. So let me start from the first reduction, from two-dimensional games to emptiness problem of two-dimensional deterministic parity automata. So here we have two-dimensional, here we have a game. So we have nodes of first player, nodes of the second player, and we can assume without restrictions that from every node there are at most two outgoing edges, and that priority function is trivial on the nodes of the second player. So what is important, what are priority of the nodes of the first player. So first of all, we will label edges by which are going out from the places of first player by A and B, and edges which are going out from the places of the second player by left and right. And now we are ready to describe automata which corresponds to this game. So its states are places of the first player, and the transition relation is defined in the following way. So, for example, what is the image of Q2A? I'm looking to state Q2. I'm looking where A is leading me, so it leads to place of the second player, and I'm looking where left and right arrow leads me. So in this case, they leads to Q2 and to Q3. So this will be a transition. And priority are inherited from the state of the game. And it is not so it is clear that automata which was constructed is deterministic, and it is not difficult to show that player one has a winning strategy from a state S if and only if automata is non-empty whenever S is declared as its initial state. So this is our first reduction, and we continue with our proof. The problem of deciding whether automata is ambiguous can be hard. We provide two more reductions. So the second reduction is from non-emptiness problem for deterministic two-dimensional parity automata to the non-emptiness problem of intersection of deterministic parity tree automata. So suppose I have two-dimensional parity tree automata, deterministic, and I define two automata, which are exactly like our initial automata, but I change only the covariant function. And for first automata, I will consider the projection on the first coordinate, and for second projection on the second coordinate. So the result are two deterministic parity automata. And it is not difficult to show that two-dimensional automata has empty language if and only if intersection of the languages of this deterministic parity automata is empty. And the final reduction is from non-emptiness problem of intersection of two deterministic parity automata to the ambiguity of parity tree automata. And again, suppose we have two deterministic parity tree automata, and we can assume that their state are disjoint, and we take another automata which is union of our automata. So the state are union, the transition relation is union, the initial states are union, and it is easy to see that automata B is unambiguous if and only if the intersection of languages of A1 and A2 is empty. So this is our final reduction, and we have proved that the problem of deciding whether automata is ambiguous is ConP-hard. Now we are going to prove ConP-hardness for other problem. So for problem where the automata is not countable ambiguous, is not finitely ambiguous, or is not boundedly ambiguous. And our proof will be, we'll use reduction from these problems to ambiguity problems. So let A be parity tree automata. We construct another parity tree automata in the following way. We add a new state F and assign minimal coder to it, and we add this transition tuple. So from new state F, when I'm reading A, my left sum should be labeled by F, and my right sum should be labeled by one of initial states. And F is declared as initial states, or the initial state of automata B. And it is not difficult to show that tree belongs to languages of automata B if the nodes of if leftmost branch are labeled by A, and the subtree rooted at the right child of the nodes on the leftmost branch are in language defined by automata A. So now we are going to prove that if automata A is ambiguous, that automata B, which we constructed just now, is not countable ambiguous. Suppose A is ambiguous, so there is a tree on which it has two runs. Now consider the following tree. Here we have leftmost branch is labeled by A, and to every child on this branch we put this tree on which A has two runs. Now on constructed tree, B has many accepting runs. It should label this branch by F, and on each one of this subtree it has two possibilities because A has two possibilities to run. So it has uncountable many choices and if we count, we have that there are at least two uncountable many runs on this tree. Let us prove other directions that if B is ambiguous, then A is also ambiguous. Suppose that B is ambiguous, so it has at least two runs on some tree, and if we have this tree, then leftmost branch is labeled by F, so the difference between these runs should be in one of the subtrees. For example, suppose they're in this subtree, and then on this subtree, automata A has at least two runs because B enters this subtree in the initial state of A. So we obtained that if B is ambiguous, then A is also ambiguous. To sum up, we proved that the following are equivalent. A is ambiguous, B is ambiguous, B is not boundedly ambiguous, B is not finitely ambiguous, B is not countable ambiguous. And from this lemma, we immediately obtain that the problem of deciding whether parity tree automata is not countable ambiguous, or is not finitely ambiguous, or is not boundedly ambiguous, is ConP-hard. And for upper bound, we can prove that the problem whether a parity tree automata is not unambiguous, or is not bounded ambiguous, or is not finitely ambiguous, is ConP complete. And our algorithm here is based upon structural characterization of the degree of ambiguity, which is very similar to those in the Buchy case. And it is open problem to find upper bound for deciding whether parity 3 automata is not countable ambiguous. For parity 3 automata, we have not succeeded to find characterization similar to the big case. Thank you for your attention.
Thank you very much for the talk. I see some hands raised. So please, Damian, ask your question.
Okay. Yes. Hi, Alex. So this ambiguity studies for our 3 automata were motivated, as you perfectly know, by this uniformization property in the monadic second-order logic. Yes, and this result of Gurevich and Shelah that the uniformization fails. So in this context, I wonder if your results could be applied to show that one can decide if a formula for monadic second-order logic has the properties of ambiguity or uniformization or some refined concept of uniformization, something like this. You could. This is not direct application, but one can think of such that you can decide if a given formula of monadic logic has this property of uniformization or not.
No, I don't see. So the problem, for example, so I consider it the problem with automata is ambiguous. You can consider a problem where the language is ambiguous. Yes. So there is no unambiguous automata which defines the signal, and these problems are completely different. So I think you asked it, yes. So your question was related more to whether the language defined by a formula is ambiguous. So I don't know how to answer your question, but for example, in this case, for automata over parity 3, we know that there is hierarchy of degree of ambiguity of languages. So as you mentioned, there are, or as you proved, that there are unambiguous languages and there are uncountable ambiguous languages and finite ambiguous languages, and k-ambiguous language for every k. But the proof the proofs of these results are completely different.
Okay. Anyone else would like to ask a question? I have an uninteresting question. What about k ambiguity for fixed k, like k equals 3?
So yes, so if k is fixed, if k is presented as in unary, then you have a polynomial algorithm. If k is presented as binary, I don't know. I have to check. Probably it is. Again, so sorry. For the case of parity 3 automata, yes, I think if k is presented in unary, then problem is can't be complete. Yes, but for other cases, for example, for Boker automata or for automata on finite words or automata on finite trees, probably there is a difference in presentation of k as unary or binary. But I don't know. I have to check. Thank you for your question.
Okay, good. Thank you. Anything else you'd like to ask about? If not, let me thank you. Let me thank once more to Alex. And now we are facing the last talk of today. It's about the paper by Guy Hefetz and Boker, and the presentation is pre-recorded. So I'd like to ask organizers to set up the presentation. The subject is discounted sum automata.
Hi, my name is Guy Hefetz, and I will talk today about the work of Udi Boker and myself on discounted sum automata with multiple discount factors. The most basic automata type is Boolean automata. A Boolean automaton realizes languages of finite words, where a word is in the language of the automaton if running the automaton on it ends in an accepting state. For example, if someone for some reason wants to model the happiness in life and tries to use Boolean automata, the result might look something like this automaton. As a baby, there is an accepting state to say that babies are happy. Growing up goes to a non-accepting state. Marriage goes to an accepting state, and divorce returns to a non-accepting state, and so on. Boolean automata are generalized to weighted automata by adding weights to the transitions and having some evaluation function for accumulating the weights of a run. One example is sum automata, in which the weights along a run are summed up. Now, instead of defining a function to true or false, the automaton realizes a function from words to rational numbers. Using sum automata, we can extend our state of happiness example to this sum automaton that measures the amount of happiness. Growing up is not that bad in this example, only -1. Marriage here adds +4 happiness, but divorce makes the person very sad, -6 in this example. Please note that there is a drawback in this model since it gives the same weight for the first and second and fifth marriage. To formalize the concept that an immediate reward is better than a potential one in the future, we have discounted sum automata, which we call NDAs, where N stands for non-deterministic. In NDAs, we have a global discount factor denoted by lambda, and the value of a word is taking the summation of the weights, but now we discount the i's weight by lambda to the power of I. So this gives more flexibility to express more involved models like our amount of happiness model, which can now express that the amount of happiness from marriage decays, meaning that the second marriage doesn't add as much happiness as the first one, and so on. Observe that NDAs realize functions from finite words to real numbers, but they can also realize functions from infinite words to real numbers. In our work, we proved everything with respect to both finite and infinite words, but for simplicity today, I will mostly stick with finite words. Automata are used to model various theoretical and practical settings, and in such models, we sometimes need exponential discounting since there are all sorts of things that behave like this. Exponential discounting is a natural phenomenon in physics. For example, nuclear radiation and temperature change have exponential decaying. Exponential discounting is also used in economics in concepts like interest rates and inflation. And of course, it is also in common practice in everyday life. Some definitions. A run is a sequence of state and alphabet letters that start in an initial state of the automaton. And when we remove all the states from the sequence, we get the word that the run is applied to. The value of an NDA on a run is achieved by taking the summation of the weights on the transition and discounting the i's weight by lambda to the I. Here you can see an example of calculating the value of this NDA on this run R. In case of a non-deterministic automaton, we can have multiple runs for every word, and every run can have a different value. The value of an automaton A on a word W is defined as the infimum value of all the runs of A on that word W. Recall that we also have infinite runs, and in this setting, there can also be infinitely many runs of the automaton on a word. So for the value, we take the infimum among all the runs rather than the minimum. There are some properties that make automata useful. For example, checking if an automaton is empty. When moving to NDAs, those properties are generalized. The acceptance of a word in regular automata becomes having a small enough value on that word. So since in Boolean automata, non-emptiness means that there is a word that is in the language, In NDAs, non-emptiness is the existence of a word with a value smaller than some threshold. For simplicity, let's say less than 0. Containment is naturally generalized to B having a value less than A on all words, and equivalence is having the same value on all words. Intersection becomes max, union becomes min, and complementation is multiplying by -1. We call the first 3 properties here decision problems and the last 3 closure under algebraic operations. Another important property is determinizability, meaning whether there exists a deterministic automaton that defines the same language. Those properties here are important since they made automata useful, especially for verification. For example, if we model the requirement as an automaton and the system as another automaton, then the containment shows that the system fulfills the requirements. Let's talk about NDAs and how they behave with respect to the properties we just showed. When considering NDAs without any limitation, prior works show that they cannot always be determinized, they are not closed under some of the algebraic operations, and there are no known algorithms for some of the decision problems. Also, some of these decision problems relate to long-standing open problems. However, when limiting the global discount factor to integer, we call them integral NDAs, and get that integral NDAs are good for all of the above required properties. In our work, we look into extending NDAs to NMDAs, where M stands for multiple discount factor. And instead of using a single global discount factor, we allow every transition to have its own discount factor. In our figures, the third element on the transition is the discount factor of that transition. We focus on integral discount factors due to the good properties of integral NDAs that we want to extend. Why do we need multiple discount factors? Well, it allows more flexibility in modeling systems when the discounting is not with a fixed ratio. Sometimes every operation implies a different discounting, for example, in Markov decision problems. Another possibility is to model cases when the discounting changes over time. For example, the value of a used vehicle. It declines rapidly in the first couple of years, and the discounting becomes more moderate in the following years. So extending to multiple discount factors allows more flexibility in such cases. Also, in reinforcement learning, where the expected return value is the discounted summation of future rewards, some of the novel approaches allow multiple discount factors. When moving to multiple discount factors, we have the following equation for the value of a run. Similarly to NDAs, we take the summation of the weights of all the transitions, but now instead of discounting by lambda to the I, we're discounting by the product of the discount factors of all the transition preceding it. As you can see in this example here, the second weight is discounted by the discount factor of the first transition, and the third one is discounted by the discount factor of both the first and second transitions. We will start by seeing the properties of arbitrary integral NMDAs, meaning without posing any limitation on the discount factors besides that they should be integers. As I stated before, integral NDAs, meaning with a single discount factor, can be determinized. The class of integral NDAs is closed under algebraic operations, and all of the decision problems are decidable. Unfortunately, it turns out that general integral NMDAs cannot always be determinized. The family is not closed under algebraic operations, and some of the decision problems are not decidable. These are all new results that we showed in our work. So if arbitrary integral NMDAs are not good enough for our requirements, we now seek a subfamily of integral NMDAs that preserve all the good properties we've seen before, and it should also extend the expressiveness of integral NDAs. I'm going to present you two such subfamilies and then define another subfamily that generalizes both of them. The first subfamily of the two is letter-oriented NMDAs, in which each letter corresponds to a discount factor. In this example, the letter A corresponds to the discount factor of 2 and the letter B to the discount factor of 3. This subfamily can be used, for example, to model systems when every action has a different discount factor. By matching every action of the system to an alphabet letter, we get that letter-oriented NMDAs is a good model for that purpose. We show that this subfamily can be determinized. When considering the same assignment of discount factors to letters, it is closed under algebraic operations, and there are effective algorithms for its decision problems. We also show that it extends the expressiveness of NDAs. The second subfamily is the family of time-oriented NMDAs, in which the discount factors is determined by the number of time steps that were taken from an initial state. In this example, you can see that every transition with an odd number of steps from an initial state has a discount factor of 2, while every transition with an even number of steps from an initial state has a discount factor of 3. A good example that can use time-oriented NMDAs is to model the value of a used vehicle, the example I talked about before. Also, for time-oriented NMDAs, we show that they can be determinized, that this class is closed under algebraic operations, and that there are effective algorithms for the decision problems. Also, time-oriented NMDAs extend the expressiveness of integral NDAs. Interestingly, the intersection of time-oriented NMDAs and letter-oriented NMDAs is exactly NDAs with a single discount factor. This leads us to tidy NMDAs, which is a subfamily of integral NMDAs and generalizes both subfamilies I just showed. In tidy NMDAs, the choice of discount factors depends on the word prefix read so far, which means that all runs on the same word prefix have the same accumulated discount factor. Here we have an example of a tidy NMDA. For every word, all the runs of A on that word imply the same sequence of discount factors. You can observe some words to see that indeed all the runs imply the same discount factors. To achieve this property of tidiness, the discount factors of the automaton need to agree with a function from words to integers. We call this function a choice function, since it chooses the discount factors of the automaton. We have that the value of the function theta on a word is the discount factor of the last transition in all the runs of A on that word. I will now point out that at a first glance, we might have a problem, since such a function from words to integers might require infinite representation. But we show that every choice function that can be used for a non-empty NMDA has a finite representation by means of a transducer. Notice that since deterministic automata have a single run for every word, every integral deterministic NMDA is tidy. And this means that tidy NMDAs can express all functions represented by integral deterministic NMDAs. Since one of the good properties we seek in a subfamily is that all the NMDAs in it can be determinized, we cannot hope for a candidate family that is more expressive than the family of tidy NMDAs. We will now see that tidy NMDAs indeed preserve all the good properties we talked about, which makes it a very nice class that in one hand is equivalent to the class of deterministic NMDAs and also contains non-deterministic NDAs. Let's return to our table from before that showed that integral NDAs with a single discount factor are good and integral NMDAs are not good enough. And indeed, we show that tidy NMDAs fulfill all the requirements. They can be determinized. For every choice function, the class is closed under algebraic operations, and all the decision problems can be solved with the same complexities as integral NDAs. The determinization algorithm is an extension of the algorithm showed by Udi Boker and Thomas Enziger for integral NDAs with a single discount factor. and we made some modification to make it also work on tidy NMDAs. And now I will show in more details the other results. The multiplying operation is simple. We multiply all the weights of A by the constant C, and by doing so, we add a factor of C for every element in the summation, meaning that indeed we get the value of A multiplied by the constant. In this case, the output NMDA has the same number of states as the input. Regarding multiplying by -1, once we have the ability to determinize, this operation is also simple. We first determinize A and then multiply all the weights by -1. And in this case, the psi blow-up is exponential, since the determinization procedure creates an NMDA with exponential number of states. In this operation, the challenging part is to show the lower bound for this size blow-up. NMDA's addition is a variant of the automata product and has a quadratic size blow-up. For subtraction, we first multiply B by -1 and then use the addition. This operation has an exponential size blow-up due to the multiplication by -1. Mean is simply taking the automata union of A and B. This is simple since the definition of the value of a word is the infimum value of all the runs on that word. For max, we first multiply A and B by -1, take their mean, and finally multiply the result by -1. And this also has exponential size blow-up due to the determinization. This exponential size blow-up might seem fishy at a first glance, since we perform determinization twice, back and forth. So one could expect it to be double exponential, but actually we show that it is indeed only single exponential. And it works due to some modification that we inserted to the determinization algorithm to make the second determinization to be more size efficient. Let's briefly see how we showed the lower bound for multiplying by -1, the lower bound for the size blow-up. For this, we use the complementation problem of regular automata on finite words, which is a problem known to have exponential size blow-up. We show a method to convert an NFA to a lambda NDA A tag with order of n state, such that for every word U is in the language of A, if and only if the value of A tag on U is less than 0. We then create an NDA for -A tag to get that for every word U, -A tag of U is less than 0, if and only if U is in the complement language of A. And finally show that there is a revert conversion back to an NFA. And if creating A tag involved with less than an exponential size blow-up, we get a complementation NFA with less than exponential size blow-up and the contradiction. I will only point out that the revert conversion from an NDA to an NFA is much harder. Upfront, an NDA is much richer than an NFA, and it is a problem to make this opposite conversion. However, for the specific values we have in our proof, we were able to show such a back conversion. Regarding the decision problems, I will shortly mention one problem, the containment, which is p-space complete. For p-space hardness, we use a reduction from a p-space hard problem on NFAs. And to show that the problem is in p-space, we present a non-deterministic algorithm that uses polynomial space. The algorithm determines B to a deterministic NMDA D, and we do this on the fly, meaning that we only keep a single state of D and use it to generate the state for the next step. This requires only polynomial space. The non-deterministic algorithm guesses a word W letter by letter and checks if this word generated is a witness for A of W is less than B of W. And to be able to do so, we maintain some property that we call the normalized difference, which on one hand can indicate that a witness was found, and on the other hand is bounded by polynomial space and also can be calculated from the previous value using polynomial space. To sum up the work, tidy NMDAs provide a promising extension to integral NDAs since they extend the expressiveness of integral NDAs. They are as expressive as deterministic NMDAs with arbitrary integral discount factors and preserve all the good properties of integral NDAs, which are determinizability, closure under algebraic operations, and effective algorithms to the decision problems. That's it. Thanks for listening.
Thank you very much for the very nice talk. Now we can answer questions. So, do we have any questions? Please raise your hand in case you have any. Meanwhile, a small question about this exponential blowups on operations on your TiD model. There were 3 or so of them with this blowup. Do you always have lower bounds for these blowups?
No, we found a lower bound just for multiplying by -1, and also for subtraction, since we use they are equivalent problems, and meaning we can use the -1 lower bound to show the subtraction. And for the last one, we were yet unable to show this exponential lower bound.
Okay, thank you.
The max operation.
Okay, there's a chance to ask a question. The last chance during this session. I will leave some time for that. I have this maybe not very clever comment. I was impressed by the number of steps you did once before you achieved your model. And you started from weights 0, 1, then generalized to rational weight or ratio. Then you cast to integer only, but still 1. Then you again generalize to maybe many different ratios for different transitions, and you again cast. Yeah, it's like several steps. Generalize, restrict, generalize, restrict before you reach your exact well-behaved model. So
yeah, I just presented it that way with non-integral discount factors. They don't behave well.
Yeah,
single discount factors. So
yes, it's like it's a generalization of this. Yeah, I agree. Yeah, I agree. Yeah, sure. Okay, there is no volunteers to ask, so you of course can ask questions offline, but still online, right? In our speakers corner. So I invite you to come to the speakers corner at Gavertown to talk more and to discuss. For now, I'd like to thank you, all the speakers, and also all of you who attended this session. Thank you very much for your time. And let's meet in a moment in the Gavertown. Thank you.